All right, so we're first going to take another look at limits. We're going to dive a little bit deeper into what it means for there to be a limit. Some of you may already have an understanding or background in limits, but I was going to start with Zenon's paradox, which is a very, very old one. It goes back a couple thousand years. You can find different versions of this, and depending on what source you go on, it has different names. Zenon was actually, and I may be mispronouncing that, was actually a mathematician philosopher, as many were. He was a Greek, and he is at least given credit by some for this, although he may not be the first one to present this problem, and we may have had solutions to this problem before he came along. The big piece on this is that we really didn't have a true mathematical solution to this until we had the fathers of calculus come along and present the formal definition of what a limit was. So you kind of have that in the back of your mind as we go through this. So you're kind of equipped with a little bit more knowledge than Zenon's students would have been when he presented this paradox to them. The idea is that we have Achilles right here, a wonderful drawing of Achilles, who of course was dipped into a lake of gold or something like that. It's a fairy tale, of course. But anyway, he was dipped in and he was made invincible and super fast, and he could run faster than anyone. He was the better warrior than anyone. Of course, during that time period, one aspect of being a really powerful warrior was to be able to run faster than anyone else and get to the battle faster than anyone else, and then still have the energy to battle. It was really more of an endurance issue than as much as anything else. And then you had the turtle, or the tortoise, I think is actually what it was. And the idea here is this tortoise can not only talk, but is actually much wiser than the great warrior Achilles. So, yeah, this is fun, right? So the idea was that the tortoise challenged Achilles to a race. And Achilles, of course, is going to accept this without a hesitation, and he's going to say, yeah, why not? I'm going to beat the tortoise. The tortoise can't run very fast. Have you ever seen an abacus turtle? Those things are extremely slow. I mean, they can weigh hundreds of pounds. They can live for hundreds of years, in fact, is what we believe. But they're very slow-moving creatures. Not necessarily like a box turtle, which actually has the ability to move fairly quickly at times for short periods of time. But anyway, so here's what we're dealing with. And the way that this works is this tortoise right here actually says to Achilles is, if you give me a head start, I'm going to win this race. Now the idea here is that we have this understood idea that whenever we run a race, we're actually running to a finish line, right? Except that's not what the tortoise is presenting in this particular problem. What he says is, if you give me, let's start off with this being a 10-meter head start. Now if you do the scaling on this, that is a huge tortoise, and that is a massively tall human being, all right? But anyway, scale aside. The tortoise says, you give me a 10-meter head start, because they knew the metric system back in the Greek days, 2,000 years ago. You give me a 10-meter head start here, and there's no way you're going to beat me, right? Because you're going to have this process here, and I'm going to be 10 meters ahead of you. And then in the next iteration, we're going to use A and T here. So the tortoise is at T, of course, and Achilles is A. Anyway, during which time, when you catch up to me at this location, so now here's Achilles, now me, the tortoise, is going to be right here. Again, ignore my scaling, right? And Achilles like, yeah, okay, so you're going to be a little bit further down the path, no big deal. And then the tortoise says, well, you're going to run to that 1 meter, you're going to close that 1 meter fairly quickly. And of course Achilles is like, yeah, I'm going to cover it really quickly. And the tortoise is saying, well, during that time period, I'm going to move a little bit further down the road. And at this point, we're just going to move over some distance. We can call it B for right now, some distance B that has been covered, right? So we're moving into this arbitrary distance that's being covered there. And Achilles is like, yeah, okay, so you're still ahead of me, but what now? I mean, so the tortoise says, well, what's going to happen next is you're going to cover that distance to where I was a second ago, but during that time, I'm going to move a little bit further. And this process is going to continue and continue, and you're going to keep covering the distance that I was, the distance that was between us very quickly. And I'm, during that same time period, I'm going to continue to move a little bit further down the path. So you see, and this is the tortoise talking, there's no way in the world you're ever going to beat me, because there's no way that you're ever going to catch me, because you're always going to be where I was, not where I'm at. And of course, Achilles is like, okay, because let's think about this. His sole attribute was he was grabbed and dipped into a lake of gold. Maybe he's dealing with heavy metal poisoning. I don't know. But he's not, his intelligence is questionable, right? So he says, okay, fine, I lose. He walks away. The tortoise wins. Everybody's happy, right? Well, Achilles isn't happy, but the tortoise is absolutely thrilled because he just beat a race with the fastest person on the planet without actually having to race him. And the underlying idea here, one of the biggest pieces, is that we normally think of a finish line going to a particular location. And we think about when we're running or when we're running a race, we're talking about speed, right? Which is a velocity and a direction, right? Another way to think of this is distance over time. But that's not the scenario that was set up here, right? We're not actually running a traditional race in the way that the turtle set this up. And the whole idea of speed and velocity is not the underlying conversation here, right? What's actually occurring here is that the tortoise is talking about, well, what happens if we're talking about this distance? Instead of us saying it's 10 meters, let's say it's just this value of d, just the distance, right? And he's saying, what if we take this distance and we let this distance get smaller, right? So the distance gets smaller. Another way, the way we write that is d goes to 0. Distance gets smaller. And what he's saying here is that this distance between us, this is the tortoise talking, the distance between us is going to get smaller. It's going to go towards 0. But is never going to get to a point where you're in front of me, nor is it ever going to get to a point where you're beside me. There's never going to be a place where that distance is 0. That's the scenario that the tortoise set up here. And this is the paradox of, well, this doesn't make any sense because Achilles is faster, so of course he's going to keep outrunning him. The difference is that you're talking about a constant speed in that situation as opposed to, I wrote that wrong. Velocity is speed plus direction. Oh well, ignore that. But anyway, we're talking about a constant velocity here. And if we have a constant velocity, yes, that distance is going to be covered in that first 10 meters and the next 10 meters and the next 10 meters. And by the time we get to the end, we have a fairly linear process that has occurred. But the scenario the tortoise is setting up here is that he's really talking about, we're not really discussing speed at all. We're simply talking about the distance that should have been covered. That distance is going to go from 10 meters to 1 meter, and then 1 meter to half a meter, and half a meter to a quarter of a meter, and it's going to keep getting smaller and smaller. Maybe by the same amount, maybe by a constant amount, maybe by different amounts, but the difference is it's always going to be getting smaller. So the distance is going to 0. This is the idea of a limit, okay? It's a tendency. And I use that term a little loosely there, right? It's a tendency, okay? What is the distance tending towards? Not what is it equal to. Notice where the equal sign here is, okay? The limit is a tendency. It's equal to a tendency. There's an equal sign there. When we say the limit, we don't really care if the distance ever becomes 0. In fact, in this particular example, it never does. So another way to think of this is that if we were to graph this out, we'd have a graph that looks like this. Say 1 over x, right? Where the domain of this is x is greater than or equal to 0. Actually, it's just strictly greater than, because we can't plug 0 in there at all, right? So when x is greater than 0, as x gets big, as the race goes on, right? Okay, so this is my y-axis, this is my x-axis. As the x values go on, as the race goes on, the distance between Achilles and the tortoise is going to get smaller and smaller, right? The y values are going to get smaller. So let's just kind of think of this from a more mathematical perspective. All right, let's look at this in terms of this. Again, we're dealing with x and 1 over x, right? So if we're talking about the distance 10, so that's 1/10. If we're 10 seconds in, if you will, and then we have 100 seconds in, so that's 1/100th. You're talking about 1,000. That's 1/1000th. Whatever that is, right? 1 over that number, so that is 1, 2, 3, 4, 5, 6, 7, 8. All right. As this number gets big, as it goes to infinity, this value is getting small. It's going to 0. And this is the underlying concept between limits in general, is this idea that as we're letting one get big, we're letting the other do some other behavior. In this instance, it's getting small. And the way we would write this is the limit as x goes to infinity, 1 over x, the function, is going to 0. Does it ever equal 0? All right, and this is a question. Does 1 over x equal 0? That's the question for us. And the answer to that is no. Okay, it's a big old fat false. Because if you multiply both sides by x, you end up, and that's how you'd solve for x, right? You'd multiply both sides by x. You end up with 1 equals 0, because 0 times anything is 0, and you end up with 1 over 1 equals 0, which is always false. So this never happens. There's never a time when this function is equal to 0. But the limit goes to 0. And that's the big piece that we have to remember about limits, is that we're not talking about, does Achilles ever actually catch the tortoise? We're concerned with what is the distance between them doing. The distance between them is tending towards a particular value. In this case, it was tending towards 0. Right? That's the underlying idea behind a limit. Okay? Thank you for watching, and I hope you've learned something. Feel free to rewind this and watch it 1,000 times if you wish.